That was just mean. No two ways about that. All right, so today's application, the last application of physics that we're going to do is the application to work. And physics students know that work is a quantity that measures a force you apply over a distance, and work is equal to force times distance. We can extend that, so that's if you have a constant force. But if your force varies, we can extend it to use calculus in order to find out how much work is done. And let's see. Physics students, in the metric system, force we measure in newtons, and distance we measure in meters. So work is measured in Newton meters, but we have a really fancy name for it. Say it loud and proud. Someone said it. That was good. That was well done. It's joules. And that's a name, not like a diamond or a ruby, but some guy named Joule. So that's a U. So it's measured in joules. And joules is a unit of energy. So the work you do is basically how much energy it takes to do something. So we're going to take a look at a problem from your classwork involving moving a chair. When we talk about how much work, we're talking about how much energy do you need to move this chair. All right? Fair enough? All right. So grab your classwork, and I think the first one, 30, we're going to have to graph it, and then we'll use this notion of work equaling force times distance to take a look at how we could use calculus to solve the problem. Oh, I'm so glad you... Gosh, I wanted to say that before we did the problem. You're absolutely right. So in the English system, as David refers to them as the annoying system, which is pretty true, force is not measured in newtons. Force is measured in pounds. So like when you get on the scale and it says like 150 pounds, it's saying, hey, the earth is pulling down on you with a force of 150 pounds. And we measure distance in feet, and work is measured in foot-pounds. And there's no fancy name for that. It's called a foot-pound. Yep. Yep, this is metric, and it's in Newton meters or joules. And the English system is foot-pounds. And to be honest, you don't have to memorize that. You'll see the units, and as long as you remember that the definite integral adds up all of these little products, you can just remember, the product is pounds times foot. And it would be you could say pound feet, but foot-pounds is how most people say it. You have to do something a little more important than just be in a class that I teach. Sorry, I didn't mean... All right, or that Mr. Tierney teaches.
Harsh.
Sorry. All right, so let's see. All right, so 30, we're going to push this chair, and it actually gives us a function, and the first thing it says is sketch a graph. So I think we should probably get our calculator out to get an idea of what this might look like. All right, so we have 20x. It's like a goodie bag? Is it like a goodie bag? Like a favor bag from a...
Why did you get enough of this?
From the alumni. Can I give you...
Oh, that's so nice.
More credits for this?
No. What is it?
I mean, it's a notepad.
Oh, that's nice.
Use the emblem watermarks notepad.
That's nice. That's really nice.
And a pen. Oh, and it's your late birthday gift.
Sorry, thank you though. So,
All right.
You shouldn't have. Thank you. Actually, you know what? This is great. No, I'm actually psyched. Thanks.
Welcome.
It is. All right. So, I went from 0 to 10, and I did 0 to 10 on my y, and then realized I had to rescale it to 0 to 15 to get the whole thing. And so this is the force that you have to apply. And notice that over the first foot, like you have to apply like a really large force, and then the longer you push, the less force you need to keep this chair moving. And this, for physics students, this should maybe be consistent with your notion of static and kinetic friction, maybe. Right? So it takes a large force to get it moving, and then once you get it moving, it's in motion. Maybe, I don't know, maybe it shouldn't even be moving this first foot until after you apply the large force, but I don't know. So maybe it's not totally consistent with our notion, but sort of a little bit. I agree. All right, so let's see. If we take this graph and remember that this is our force, and this is our distance. Then, if we want to find the work that was done in moving the chair from 0 to 7 feet, what we're really saying is 1, 2, 3, 4, 5, 6. Find this area, right? Because that area is going to be the force times the distance, but it's going to be in calculus form. So for those of you in physics, you just do it when there's a constant force. When there's a variable force, you need calculus to say, hey, add up all the forces, and instead of distances, we're going to take the force over really small distances. What are we going to call it? dx. So force times dx, where dx represents a really small distance, and F represents the force. And let's see, if we want from 0 to 7, we'll just do from 0 to 7 of 20x e to the negative 0.5x dx. And there it is in calculus notation. So what this says is the work is equal to all the forces times little infinitesimal distances from 0 to 7. And that's exactly what the work is. And once we set it up in calculus notation, now we can go ahead and calc 7. All right, from 0 to 7, and we get 69.13.
Does it matter when we say joules or foot-pounds?
All right. So we actually have to go back and we have to look at the units here. Force is measured in pounds, distance is in feet. So this tells us we have to say foot-pounds. So there's the force. There's the work that's been done. And that's a measure of how much energy it takes to move this chair. Is that all right? So for physics people, I'm guessing that makes perfect sense. For someone who hasn't taken physics, do you want to ask a question? Because that's probably like a new concept, maybe.
I think conceptually, I think that's the word. It makes sense because you have to put in more effort when you're just starting it off.
All right, good. The thing is, we're going to get different functions for different things. And sometimes it's going to be like linear, and it's just going to take more force the more you push. Other times it'll be like this. It'll sort of drop off as soon as, you push it. But the important thing is, whatever the force is, you just need to know that work is going to be adding up all the forces times infinitesimally small distances. A bonus question for physics students. Not for calculus students. I guess you could try if you wanted to. Sorry. All they're going to get is meaningless praise. If instead of distance, I measured this in time, what would I be measuring here?
Right.
Nope.
Power keys.
Nope.
Money. No purse.
Work.
Nope.
Velocity.
Nope.
Position.
Newton meters.
No.
Oh, I got it. Force times time.
Okay, you're absolutely right.
Newton meters per second.
It is going to be force times time, and if you see force times time, my physics students should actually be thinking right now, like, oh, I know what force times time is.
I should know what force times time is. I don't.
Come on, where are you, physics students?
Mass times acceleration time. Or mass.
Yeah.
Okay. That is impulse. Force times time is impulse.
Right.
That was a while
Okay.
ago.
Yeah, that was.
Or you could say it's momentum.
They're not getting praise.
No praise, no meaningless praise for me. All right, and then for C, if you continue to push the chair and it continues to move, what limit would the amount of work approach as x approaches infinity? Now be careful, there's a right answer and a wrong answer. What's the wrong answer? 0 is wrong. The work doesn't approach 0. What approaches 0? The force approaches 0. So as the force approaches 0, can you see that the work is going to get closer and closer to something, but it's going to be bigger than 69, right?
It's infinity.
All right, so that's the question. You keep adding on. Think about the definite integral, right? We keep adding on little bits, and the question is, does keep adding on mean it's going to get infinitely big, or does keep adding on mean it's going to get to a limit? And I don't know. I mean, sometimes when you add on, it gets bigger and bigger and bigger, right?
I mean, eventually, if the limit of that function is 0, it's going to keep going on and on forever.
I think it goes to a limit.
Right. Now, look, just if you take 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, right, we're going to keep adding on more and more and more, but you know that sum approaches, the term approaches 0, but the sum actually approaches 2. Right? You're at 1, you're going to go halfway to 1.5. You're going to go halfway to 1 3/4. You're going to go halfway to 1 7/8. You keep getting halfway closer to 2. 2 is your limit. So, from sequences of series at the end of last year?
Huh?
No, don't say huh. I mean, you can be like, oh yeah, I forget. But,
I don't
right,
remember.
sequences and series.
I don't know. I guess I did my
Yeah, he was.
Good.
I did my glasses.
Glad to hear it.
I mean,
I thought I did very nice.
I'm gonna read it.
Let's see.
I did like pretty good.
Instead of doing it on a graph, I'm going to do Math 9. And I'm going to take y1 variables x from 0 to, how high do you want to go up? I'll start with 100, David. So if I find out how much work was done from 0 to 100, it tells me 80 foot-pounds. Don't you think that that's probably a limit? Just a guess. If I do from 0 to 200 feet, it's going to do twice as much work, and it tells me, look, you hit 80. 80 is your limit. Okay? So the limit to the amount of work you need to do is 80 foot-pounds. All right?
So, is there a way to that? How can you calculate?
So right now the question's like a calculator kind of question. What we've just been given, Alicia, is something called an indefinite integral. What I actually asked you to do was say, tell me what happens when you add up from 0 to infinity 20x e to the negative 0.5x. And that's not something that you know how to do this year. If you take a second year of calculus or a second semester of calculus at college, you'll learn that. Okay? Okay. Questions on that? You all right? All right. Next, same concept, but a slight variation. Actually, all these are the same concept, slight variation. And if you look at 31, we have a spring, and our physics students know lots about springs. The problem is I'm doing first semester stuff for you, right? So if we want to do the potential energy stored in a spring, 1/2 kx squared, right? What I want to talk about is not the potential energy, but the force And if physics friends know that there's a law, Hooke's law, you don't have to know it's Hooke's law. But what Hooke's law says is the force that it requires to stretch a spring is equal to kx, where k is some constant. It's called a spring constant. And x is the distance. And so what this actually says is, hey, to stretch a spring, the force is a linear function. It's kx. The more you stretch it, the harder it is to pull. That's what it says. And it's a linear thing. Right? So the more you stretch, the harder it is to pull, the more force that you need. So if you talk about work for a spring, work is still equal to the definite integral of f dx, but for a spring, specifically, it's kx dx. So the first example... What are you doing? So the first example had, sort of this interesting force function, 20x e to the negative 0.5x. If you're dealing with a spring, it's actually a really simple force function. It's just kx. And the only work you have to do is find out what k is. All right, so we can actually do that. 31 says, a relaxed 10-inch spring requires a force of 25 pounds to stretch it 0.25 inches. So, look, force is equal to kx, right? I know that. I know it takes 25 pounds to stretch the spring 0.25 inches. So, in this case, for this spring, what's the constant?
100?
I'm thinking that's 100. 25 divided by 0.25, k is 100. So, oftentimes, the first thing you have to do when you're dealing with springs is finding out what the constant is. Now that I know the constant, I know that the work done is going to be 100x dx, because I know that this is the force to stretch a spring. And that's true always. Whenever you're stretching an ideal spring, the force is always kx. Alright, so now I have to figure out how I'm going to stretch this spring. Part A says, calculate the work done in stretching the spring from 11 to 12 inches. Now, there's a wrong answer here, which is the obvious answer, and there's a right answer, which is not so obvious. So here's your 10-inch spring, and we're going to stretch it from 11 to 12 inches. So, wrong answer, what would the limits of integration be for the wrong answer? 11 to 12. Seems perfectly obvious and perfectly makes sense, but it's wrong, because we're not actually stretching the spring 11 to 12 inches from where it is now. We're stretching it 11 to 12 inches, but it starts off at 10 inches. So, alright. Morgan has it. Right? I'm actually stretching it from 1 inch to 2 inches because 10 inches is really equivalent to stretching it 0. If I stretch it 0, it's 10 inches. If I stretch it 1 inch, it's 11 inches. So 1 to 2 is 11 to 12. So Morgan got both answers. You got the wrong answer and the right answer. Nice job. Are you a physics friend? You should take physics. Oh, really? All right. Maybe next year. Yeah. What do you want to be? Oh, no? No more math and science for you? What's it going to be? It's all right. Yeah, I get very few students that come back and are like, oh, yeah, I'm taking tons of math courses. I love it. I'm going to be a mathematician. Usually it's like, oh, I'm taking great history courses, and I love this English literature course. Thanks, Alicia. All right.
What other math classes do you teach at Curiosity?
This year?
Yeah.
Pre-calc and calc. I think I've taught just about everything, though. What? No, I haven't taught geometry in a couple of years. I haven't taught algebra here. I taught at my first school. I taught Algebra 2 and Algebra 1, and I've taught 5th, 6th, 7th, and 8th grade math too. Yeah. You gotta like. I'm not saying as a student. As a student, maybe it's totally fun. As a teacher, you like have to love that age group. It is a hard age to love from an adult's perspective. Yeah. All right. Hey, just
wait. What is it, like 4 years?
Oh, I'm not looking forward to it all. Believe me. Like right now is awesome. Like 4th grade, like 3rd. You know, my son's in 3rd, my daughter's in 1st. Like it's awesome. And here's the saving grace: is that when they become like obnoxious teenagers, middle schoolers, like I'm going to have a new baby now who's going to be like I'll be able to relate to a little bit. Well, I'm not going to ignore them. They're going to ignore me, right? Isn't that what you all do? Like when you turn 13, like you just drop your parents, like you're like forget it. Drop me off here a block away. Oh, that's nice. All right. All right. For part B, I would just change the limits to what? 2 to 3. All right, so Morgan's totally with me. Thanks. All right, one last variation on a theme, and maybe we'll time it right so we get the last problem done, Julia's hair is finished, and the bell rings. Did you do all that right now? That's impressive. Man. All right.
I'll have to do it for softball. I'm still paying attention.
No, I'm fine. I'm totally fine. I think I was right, Dan. I mean, this is a great class. You guys really are just beaten down by the full day of school, and so you're just like mellow, and I don't know if you're understanding anything, but it's great. All right, so last variation on a theme for work. We're going to lift a safe, and it's on a 100-foot cable. This is the safe.
Okay. Oh, if you grab a bank, they're not going to call it slack,
All right, so if we were just lifting the safe, the work would be that we have to do would be force times distance, and the force that the safe is pulling down is
mg.
It is mg, but we're in pounds, so it's 500, and the distance would be 80. So it would just be, 4,000 foot-pounds? But we're not just lifting the safe. What else are we lifting? We're lifting the cable, and here's the thing about the cable.
It gets lighter and lighter as you go higher and higher.
Yeah, the more you pull in, the less it weighs.
Oh, that's rude.
I like magical weightless cable.
That is rude. All right, so here is the safe. The safe is 500. I know I'm going to have to pull that in, so I'm going to have to exert a force from 0 to 80. Plus, I have the cable. Now, do you agree that the cable is going to be something times 5?
Yeah.
Because if I have all 100 feet of it, it's going to be 100 times 5, which is 500. But by the time I get to 80, how many feet do I have left? 20, right? So I need something in here that's like, so look, here's the safe. Here's the mass of the cable. I should say weight, sorry. Weight of the cable. And I need something in here for the length of the cable, but what's the problem with the length? It changes. So I need a function that describes the length of the cable. And it's going to be hard. No, close though.
What did you say?
Closer.
100 minus y?
No, you got it. 100 minus x. Because I know it starts off at 100, and whatever x is, whatever this length is what I'm subtracting. So, look. When the safe is at 0 feet, right, when it's down on the ground, I plug 0 in. How many feet of cable do I have to lift? 100 minus 0, which is 100. When I've lifted the 80 feet, how much cable do I have left to pull in? 20. 100 minus 80. So, man, Morgan, you're just on fire today. So look, you can do that by hand. You can do it with your calculator. The important thing here is the variation on the theme was the force was a combination of two things. The force was the safe and the cable was a variable sort of function. And here's the great thing. Morgan sort of set us up with a template, right? 100 minus x gives us the length of the cable times the weight of the cable, which they gave us here is 5. And I don't want to do it, but just to read it so you can see how similar it is. 33 says you have a spaceship at a launch pad and it weighs 30 tons. By the time it's at an altitude of 70 miles, it weighs only 10 tons because it's burned fuel. Do you see how that spaceship has sort of, it's almost the same as the safe? The higher it gets, the less it weighs. Right? So again, it's going to be very similar to sort of the template that Morgan and David helped us shape. Okay? So look, it's your home is H5C, and it's all variations on work is equal to force times distance. All right. Oh man. Hey.
Did you just think of that, or did you have that planned all day?
All right. I didn't have it planned all day.